Hello, welcome to our next set of stats notes. We're on section 4.3. This section we're going to cover a couple things. First off, we're going to start with the at least once rule. There are a lot of times with probability where you don't need something to come up right more than once. If it just comes at least one time, you're happy. Think of like buying lottery tickets. You buy at least one winner, you're happy. It's okay to have two winners. It doesn't hurt anything. You still get the same winnings. If you buy raffle tickets, again, if you have more than one winner for different raffles, that's great. You're not going to be sad. So lots of situations where at least one of the things need to come up the way you want them to. And if you get that at least one time, and more is okay, but if at least one time it comes up, then you're happy. So we're going to be dealing with a lot of situations where we want at least one occurrence. So at least one time for that to happen. Note, that's the same thing as saying one or more. So at least one, it could be one, it could be two, it could be three, it could be four. It just has to happen at least once. Also, the opposite, the complement of at least once is going to be it never happens. So if you buy 20 lottery tickets, at least once, one of them has to be a winner at least. The opposite is going to be that none of them are winners. So the complement is no occurrences. No winners is the complement. So one of the tricks for finding at least once with probabilities is to actually find the probability of it never happening, and using that rule we said earlier that from the previous section that the probability of an event happening is equal to 1 minus probability of it not happening, the complement. So we'll use that rule a lot when we're doing these at least one problems. So at least one problems deal with probability of something happening at least once, but we usually find them and find the probability of it not happening at all. So let's look at our first example. So this problem says, find the probability of drawing two cards from a deck and getting at least one queen. So we're looking for at least one. There's at least one thing. So the first one could be a queen, the second one would be a queen. They could both be queens. All that would be good. We're looking for at least one queen. And you can see why we wouldn't want to do this directly and trying to find the probability, because what do we look for? If we said the first one could be a queen, or the second one could be a queen, or they could both be queens, like it gets kind of complicated. So it's easier to do this, to find the probability of at least one queen by actually doing 1 minus probability of no queens. So that's going to be the easier way to do this. We're just going to find the probability of not getting a queen at all, subtract that from 1, and that'll give us the probability of getting at least one queen. Note we are drawing two cards, and we're going to say this is a standard 52 card deck. So notice that we'll have 52 cards total to start with. So when we do this, since we're drawing two queens, we're going to have to do this in two parts. We're going to have the probability of the first one not being a queen, and we'll have to get the second one also to not be a queen. So we're actually looking for two non-queens, two cards to be not queens. Again, we're doing this because we're subtracting from 1. That's the complement so that we can get at least one queen. When we do these and probabilities, especially in cases like this where we're drawing cards, got to be careful. Here, we're going to probably assume that there's no replacement. Usually when you're playing cards, you don't put cards back. So unless it says something about replacement, you'll assume that there's no replacement. And that means this is going to be dependent. Dependent probabilities are when you have to worry about kind of changing the probability after the first thing happens. So to find the probability of not a queen and then another not a queen, we'll do this with the multiplication rule where you find the probability of the first one, not getting a queen, and then we multiply. There's a probability of getting the second one not a queen, but since the first one was also not a queen, we're going to do the second one not a queen, given that first one was not a queen. So remember, remember that we tweak the second probability. We kind of take that, we change it a little bit because the first thing happened, and then change the probability for the second part. Okay, still doing subtracting this from 1, because again, that's how we get the probability because we're doing the complement. Okay, so the first one not being a queen, well, there's 52 cards in the deck, so we're looking at 52 cards, and there are 4 queens. Remember, there are 4 queens. So there are 4 queens. So the probability of not getting a queen, well, that means if you take away the 4 queens, there's 48 cards that are not queens. So the first thing we do, there's 48 out of 52 chance that the first one's not a queen. Now we're going to assume that worked, that we didn't get a queen the first time, and we're like, okay, what's the chance of getting not a queen the next time? Well, since we already didn't get a queen the first time, there's one less non-queen card. Whatever we got the first time, that card got pulled out. So now there's only 47 cards left that are not queens. Also, we took a card out of the deck, so instead of being 52 cards left, now there's only 51 cards left because we removed a card from the deck. So that's what we're going to subtract from 1. So again, this is probably getting not a queen the first time. There's 48 non-queen cards out of the 52 total. We take that card out, and so the next time we say, okay, now there's only 47 non-queen cards left and only 51 cards left. And so that's probably the second one. And it's all because it's dependent, so we had to do that, changing the probability. So we'll type that in our calculator, and we'll get this probability. So we do 1 minus 48 divided by 52 times 47 divided by 51. We're going to type it in all at once. The multiplication should happen first because calculators are built with order of operations, so they know to multiply before you subtract. So I should be able to just type that in, and it'll give me my decimal. And a lot of times these ones will be decimal, so you put in something like 0.149 into MyLab, or they might ask for a percent, so you might take that and turn it into 14.9%. Round appropriately, so MyStatLab will tell you what to round to, so just make sure you round to the right appropriate number. So this is finding the probability of at least one thing, but again, we don't do it right on. We don't find the probability of getting at least one, we find the probability of not getting it and subtract from 1. Let's try another one like this. This time we're going to deal with dice. And I didn't specify, but we'll say we're rolling 4 dice, and we're going to say that these are 6-sided dice. I should have been better about saying that on my notes, because not all dice are 6-sided, but I kind of tend to just assume I'm using 6-sided dice. So we're going to roll 4 dice, they're 6-sided dice. We're going to look for at least one. There's that at least one again. At least 1 5. Just trying to find the probability of at least 1 5. And again, I'm not going to do this straight on. Instead of trying to find the probability of at least 1 5, I'm going to find the probability of no 5s, and I'm going to subtract that from 1. So I'm going to do 1 minus the probability of no 5s. That's what I'm going to do this. Now notice with these 5s, with rolling these dice, when you roll dice, they don't affect each other, right? The first roll does not affect the next roll. So these are going to be independent. And remember, with independent, we don't have to change the probability. So this will be a little more straightforward because every time we find a probability, it's just going to be the same each time. It's not going to change at all, which is kind of nice. Okay, so probability of no 5s. Well, since we're rolling 4 dice, we're going to have both the probability of the first non-5 and the second not 5, and the third not 5, and the fourth not 5, because each one of these needs to be not a 5, right? Because we're doing the opposite, not a 5. Instead of looking for 5, we're looking for no 5s. And we're doing 4 rolls, so we have to do this 4 times. Since these are independent and we're doing that multiplication rule, remember with independent, you don't change the probability, so we just find the probability of each one separately and just multiply them together. There's no need to worry about given multiplication, the given probabilities here, because the first one's not affecting the next one. So each one of these is going to be the same probability of not 5 times P not 5. Okay, so subtraction from 1. So what's the chance of the first time I get not a 5? Well, since there are 6 sides on this dice, there's 6 total, and only one of them is a 5, the other 5 sides are not 5s. That's kind of weird, but yeah, it's because there's 5 other sides on a die, right? Besides the 5 we're trying to get in this case, but not get over here. Okay, so but again, same thing over here, because not 5 does not change because the probability doesn't change. So this is still going to be 5, 6, as is this one, as is this one. So when you're doing independent problems like this, when they're independent, when they're not changing over time, it makes it a little more straightforward. You just find the same probability each time. Because this happens, you can actually take this and rewrite it. We can do 1 minus 5, 6 to the 4th power, because we have 1, 2, 3, 4 dice that we're rolling. We end up doing that 5, 6 4 times, or to the 4th power. So you can do it like this, and this is kind of the way people typically do it when they're working with independent probabilities, is they do the 1 minus whatever the probability is. So in this case, 5, 6. I'm going to type parentheses 5 divided by 6 to make sure that that power of this 4, when I do power 4, is on that whole 5, 6. So you want to make sure you use the power button to get your power, and yeah, use your parentheses around that 5, 6 to make sure it goes in there. Right. So I'll hit that, and now it'll tell me the probability. So this is the probability of at least 1 5, because I did a complement, no 5s, subtracted from 1. That's how I get at least 1, because it's the opposite. So that's how we did that. And again, each one of these 5, 6s each one of these 5, 6 was a different roll. So we had 4 of those rolls because we were rolling 4 dice. So that means that the chances we have 0.5177 or 51.8% chance. So that's the chances. Better than 50% chance that at least one of those 4 dice are going to come up with 5. So they're pretty good odds, 50-50. Every other time you expect at least one of them to be 5. That's the at least one rule. Now this method right here, where we find the probability of not getting it, so 5, 6 is the probability of not getting what we're looking for, and subtract it from 1, and then we just do a power for how many tries, this actually turns into a formula. So we actually have a formula for the at least once rule if we're doing independent trials. So if they're independent, so this, the probabilities are not affecting each other. So if they're independent trials, we can find the probability of A, which is getting something at least once, in n trials, n is the number of tries, where the probability of getting it is P, probability is P, then this is our formula. So the probability of getting it at least once in n tries is 1 minus the 1 minus P. Well, what's 1 minus P? Well, if P is the probability of getting it, then 1 minus P equals P complement, or the probability of not getting P. So we actually just have right here, we have the probability of not getting it to the power, where n is the number of tries, and subtract that from 1. That's what we just saw on the previous page, where we have the 5, 6 was the chances of them getting the 5 to the power 4, because we had 4 tries subtracted from 1. So we do, the power of not getting it, the probability of not getting it to the power, where's the number of tries, and subtract that from 1. So let's show an example using this. So this example, they have, suppose you're designing a backup system for NASA. So NASA wants a system to back up something. The original system has a 15% failure rate. So there's a 50% chance of failure. That's your failure rate. And so does your backup system, right? So both of them have a 50% chance. That's not changing. Find the probability that at least one system will stay operational. So notice they're actually looking for the chances that it will stay operational. So we want to find the probability at least one works. Note, first off, there's 2 parts, right? There's the original system and the backup system. So the number of things we're actually working on is going to be 2, right? There's going to be 2 systems, the first system and the second system, the original system and the backup system. So there's going to be 2 trials, because we have 2 trials for the system to work. If the first system works all the time, we're happy. If the second system works all the time, we're happy. We're only unhappy if they both fail, right? That's why we have 2 tries. Also notice that we're looking for the system to work. So P in this case would actually be a probability that it succeeds, that the system works. So this 15% is not P. 15% is actually the probability that it doesn't work, the opposite. So this 15%, or if I write it as a decimal, 0.15, that'd be the probability of failure. In this case, P, probability of success, would actually be 1 minus 0.15 would be 0.85, or 85%, because it's the rest of the 100%. So there's an 85% chance that it succeeds, there's a 50% chance that it fails. So it works is 85% chance, and it fails is a 15% chance. Okay, so using the formula, the probability of at least one works is equal to 1 minus, and again here we're going to take the opposite of P, so we're not looking at P, we're actually going to look at P prime, or the P complement, which is a probability that it fails. So we're going to put in here that P fails, which is actually 0.15, the probability it fails. And we're going to do it to the power of how many tries we get. Well, in this case, because we have n equals 2, we're going to have that 0.15 to the second power. That's what we're going to subtract from 1. So probability of failure, so even though we're looking for it works, we're doing the opposite. So we find the probability of failure. The power is how many attempts we get, how many machines we have, and then subtract that from 1, and now give us our value. So it'll tell us, how likely we are that at least one of them will work the whole time. The mission's safe. So if I do 1 minus 0.15 to the second power, I end up with 0.9775. So this becomes 0.9775. If you turn it to percent, it'd be 97.75%. pretty good, right? 97% chance this succeeds. That's pretty high chances. But it's not maybe enough for NASA, right? Because NASA, they don't want their rocket like blowing up halfway through, or they don't want it failing. So they might look at that, 2% chance and say that's too much for us. We want even better chances. So they might say add a additional backup. So what if they come along and they say additional backup is added, and then they want to know what are the chances at least one system would be functional. So this, at least one of these will work the whole time, because now instead of just two systems, we have three systems. So they're going to ask that. So on this one, we're going to do the same thing. We're still doing probability of at least one works, right? So we want at least one to work. So to do that, we'll find the probability of 1 minus probability that they all fail, right? We're looking for failure. And then again, the power is going to be n. But the difference here is because we have an additional backup, n is now changed. N is actually 3, because now we have the original system, the first backup, and the second backup. So we have two backups. So the n is now 3. So to do this, we're going to do 1 minus, again, still p complement of the probability of failure is 15.15. So that's the probability of failure. But now the power is going to be a 3. So all that really changed is we add in the backup, so we increase the power. We have more things. What we'll see is because we have more backups, the probability that it's going to work is going to go up. So this is actually going to get less, because when we subtract from 1, this will leave behind a bigger number. So let's try this. Now to type this in, here's a little trick for you. If you want to retype the thing you just typed, you can hit the second button and hit the enter button down here. So it does the entry, and it re-enters the last thing you entered. And it's a nice way to retype what you just typed. And then you can cursor back, arrow back to where you want to change. So I want to change that 2 to a 3, and just type a 3 over top of it. And it saves me having to retype everything. I love that option, because you can go back and just retype the last thing and then just tweak it a little bit. So that shows me that the value for this one is 0.9966, or 99.766, I'll say 66%. Again, my lab will tell you, how much to round to on a problem, or whether they want the decimal or the percent. I'm just giving both up here just to make sure you can see how to get either one. And then you can see this actually went up a little bit, right? So instead of 97%, now that's 99%. This is less than like 0.5% away from 100. So this is pretty good chances that at least one of those three devices will work. And that's what you'll see in real life in NASA. They'll have two backups for every system, because that just makes the chances of failure of that system so much slimmer. If it's a super essential system, they might even have a fourth backup, or something, just to really make sure it's really hard for it to fail. And that's what they do. The more backups you add, the just less likely it is going to fail by the end of the mission. Okay, let's do two more of these, and then we'll show a different part of the section. So let's do two more at least once problems. So here we go. It says a drug company is testing a side effect from a new pill. They say there's a 7% chance that the test subjects will experience the side effect. So there's a 7% chance you're going to get the side effect. What is the probability that at least one, so we're looking at least one of their 12 test subjects, so you can see that they're doing 12 trials, 12 different people are taking this drug. What's the chance that at least one will experience the side effect? So again, we're going to use that rule. We're going to do 1 minus the probability that, since we're looking for experience side effect, in this case, the opposite would be not, right? So this would be no side effect. And we'll do that to power n, where n is the number of trials, right? That's our probability, of at least one. Formula, 1 minus probability of not getting it to the power n. So in this case, n would be the 12, right? Because there's 12 test subjects, so there's 12 trials. Probability in this case, so p, again, p was probably that thing happening that we're looking for, so we're looking for the side effect. So p would be 7%, because that's the chances of it happening. The complement not getting the side effect, that means that's actually 93%, right? Because there's a 7% chance you get the side effect, there's a 93% chance that you don't get the side effect. So to find the probability of at least one with the side effect, we find that by doing 1 minus the probability of no side effect into the power n. Again, n is 12, so the power is going to be 12. probability of not getting the side effect, we said is actually this 93%, because this is side effect. This is no side effect. So that's going to be 0.93 to the 12th power. And I'll subtract that from 1 to find the probability. So again, since we're looking for the side effect, we find the probability of not getting it. That's what always goes in here, the probability of not getting it to the power, and that's what we subtract from 1. We're doing the complement again. To find this, we'll do the opposite. So let's type that in a calculator. We get 1 minus 0.93 to the power of 12. It's 1 minus 0.93 to the power of 12. And we actually get a 58% chance. So there's a decent chance. There's a 58% chance of 0.5814, which would turn into 58.14%. There's a 58% chance that this will actually come out with with one of the people having the side effect. Because there's 12 people in the study group, we're pretty likely that at least one of them will have it. That's what this is telling us. Okay, let's try one more. The gambler's playing cards, and he needs one more ace to complete his set of 3 aces. So notice that he's got 3 aces already. He started with 3 aces. He wants one more ace. If the dealer has 3 cards left to deal to him, so I guess they're playing a card game with 6 cards, I guess, what are the chances that he will receive at least one more ace? So he's looking for at least one more ace. Now notice this one. This one's a little different because this one, when you deal cards, you typically don't give them back, right? You typically just keep your cards. So this one's actually going to be a dependent. And we said that formula we were using, that at least one formula, was only for independent. So this one, dependent, we can't use the formula. So we kind of have to go back to the first one we did and remember that we did use the complement. So to find the probability of at least one ace, we're still going to use the complement. We're still going to find 1 minus the probability of no aces. But this time, instead of being able to use the power and do that, the probabilities are going to change each time because every time you get a card, you're going to have different chances of what you get. So this one, we can't just use the power and say the probability just matches every time. This one, we're going to have to kind of do this out. So we'll still have 1 minus. Probability of no aces. Well, since we get 3 cards, right, the dealer has to deal 3 cards to him. We're going to look at probability of not an ace, the first card, and not an ace, the second card, and not an ace, the third card. So we're looking for all 3 cards to not be aces. That's going to be how we do this. And since this is dependent, each probability is going to change. So when we do the first probability of the first ace, it's just the typical probability of no ace because we haven't done anything else yet. But when we go to do the second card, we do the second one, we're going to do probability of not ace, given the first one wasn't an ace. So the first one wasn't an ace already, because they already drew 1 card. We go to the third card, we're still going to multiply. We're still going to find the probability of not an ace. Now this is given that the first and second were not aces. So we actually have that times 2, right? Once for the first card, once for the second card. So now we have to worry about that happening twice. So this one, when we're doing this and probabilities, we have to think about how the probability changes each time. So the first time, I think about, okay, they used up 3 cards here, right? Used 3 already. So those 3 cards are gone. So instead of 52 cards in my deck, right? Typically you have 52 cards in your deck. We'll say, okay, the 3 of them are gone. So we are actually left with 49 cards. So there's 49 cards left. And out of those cards, how many are not aces? Well, they took out 3 aces. There's 1 ace left, so there's 48 other cards, right? There was 4 aces to begin with. 3 of them are gone already. There's 1 ace left, so there's 48 cards that are not aces. Okay, then we go to the next one. So, okay, now we want to try another not ace. There's only 48 cards now, because we took a card out in the previous draw. And since the card we drew out was not an ace, these not ace cards are down to 47. There's 1 less of those not aces. Then we go to the next one and say, okay, now we want to draw another card, but now we've already taken 2 cards out, so we're down to 47 cards left. And the first 2 we took out were both not aces, so there's only 46 cards that are not aces left, because there's still only 1 ace to be had. Okay, so this becomes 1 minus that multiplication. Again, we couldn't do the power because each one of these changes because it would be dependent, since we're not putting the cards back. Now, if they'd given us the same problem and said, But each time you put the card back, well, then this would have been able to use the rule. We would just have the first number to the third power. But because we don't put the card back, the probability changes each time. Okay, let's find this result. So we get 1 minus 48 divided by 49 times 47 divided by 48 times 46 divided by 47. And it gives us 0.06122. Not very good chances, right? Because there's only one ace left, there's a lot of not ace cards. The chances of getting an ace are pretty slim. It's only a 6.122%. So not very good chances of getting an ace. It's pretty unlikely for this one. You're probably not going to get an ace. Okay, that's the first big part of this section. There is one more part that's a little different, and this is dealing with conditional probability. So conditional probability is when you're looking for a probability, but there's a condition that's happening before you find the probability. So it's kind of like given probabilities, and we'll use similar notation. But what this means is you'll be looking for the probability of an event, but you know some information about what's happening. So for example, maybe you know you want to find the chances you get an A on the exam, but you know that you passed. Or maybe you saw enough of the card you're being dealt to know it's a red card, and you're looking to see maybe if it's going to be hard or not. Or, if you are wondering if you won the Powerball and you know that, your first two numbers match, but you don't know what the rest do, what are your chances of that? So you kind of have some foreknowledge, some information. Now there is a formula for doing this. There's a formula for finding the probability of, A given B. So B is going to be the kind of the foreknowledge. And you do it by doing this. For the probability of getting both A and B divided by the probability of just B, the second part. Now this formula, we can use this to find the probability, this conditional probability. Now one problem is this formula actually makes things more complicated, and it makes it a little bit harder. So when you want to find the probability of event A, if we know event B is true, you can use this, but it actually makes it more complicated. I'll show you maybe the easier way after we show just once with the formula. So we'll show the formula. I'm not really going to require you to use the formula. You can do it however you want. So if you think the formula is easy and you want to use it, that's fine. But if maybe you see my other method, you might think that's a little bit better. So let's look at an example. Suppose a person draws a card from a standard deck. Again, standard deck, that's 52 cards. Find the probability that a queen of hearts is drawn. So you're looking for a probability of queen of hearts. So queen of hearts. Oops. Given, we're going to do that first. Yeah, do that first before we do the second part. There's two steps. I always forget there's a second step. So we'll do that first. Find the probability of queen of hearts. Well, first off, there's only one queen of hearts, right? There's only one card that is the queen of hearts in the whole deck, and there are 52 cards in the deck. So the probability of the queen of hearts, that's 1 out of 52. That's pretty simple. But then we're going to look at the probability of getting the queen of hearts given the card is a red card. So we know we got a red card. What are the chances of the red card is the queen of hearts? Now we're doing the probability of the queen of hearts given it's a red card to start with. Okay, so using the formula up here, what we do to find the probability of queen of hearts given red is first off, we find the probability of being both. It would be both queen of hearts and red. Well, there's only one card that is both, right? There's only one queen of hearts. There's only one card that's both queen of hearts and red out of the entire deck of 52 cards. So there's only 1 out of 52 chances. We just did there. But then on the bottom, we find the probability of B. And the probability of B in this case is probability of being a red card. Well, what's the chances we get a red card? Well, there are 26 red cards. Half the deck is red, so half of 52 is red out of the 52 cards total. So that's the probability formula. Now we do have to simplify this. Remember that when you have a fraction divided by a fraction, you can always turn it into multiplication. You leave the first one alone and you flip the second fraction. So I'm going to flip that one over and turn it into 52 over 26. So dividing by a fraction, you can flip and multiply. And then what we can do is, because we have two fractions being multiplied, you can cancel, you can cross cancel. So we can take something like 52 and divide both of these by 52, and they cancel away, and we're just left with ones on the top, and 1 times 26, which gives you 26 on the bottom. And that is the answer on this. The probability of getting a queen of hearts, given that you know you're getting a red card, would be a 1 out of 26. But the easier way, so without the formula, you could actually do this without the formula, is to just think about the requirement they gave you, this red requirement, and use that when you're doing a problem. So instead of trying to do this whole process to find the probability of getting the queen of hearts, given we know it's red. What we do is just think off, okay, first off, how many cards are Queen of Hearts if we're only looking at red cards? Well, there's only one Queen of Hearts, so there's only one Queen of Hearts. And then think about the fact that we're only looking at red cards. So instead of looking at the whole deck of 52, look at just the red cards. Well, how many cards are we working out of then? We're only working out of 26 cards. So you can see that red kind of gave us the bottom number, right? Because that's how many red cards are. And you notice that this matches what we just got. So this is a way to do that without having to do all that fraction junk. You don't have to worry about these fractions and simplifying all that. You can just say, okay, when I think about this, if I know foreknowledge about the reds, given the reds, I think about how many options are good out of the reds, and then how many reds are there, and that works. Okay, let's try another example so you can kind of get the idea. This one is about a college stats course. There's 24 women, 18 men, 22 of the women are passing, and 16 men are passing. They want to find probability A given B, where A is a student is passing, and B is a student is male. So we're actually looking for the probability that they're passing, given we know that the student we're talking about is going to be a male student. That's what we're looking at. So instead of doing the fractions, what we're going to do is we're going to first off think about, if we're looking at males, how many males are passing? Well, there are 16 males that are passing, right? So we have 16 people that would fit both criteria. They're both male and passing. That's going to be our top number. Then we look at the bottom requirement. So instead of looking at all the people, we look at just how many students are male. Well, there are 18 men in the class, so the fraction becomes 16 over 18. And that's it. That's your answer. You could simplify. You can divide the top and bottom by 2 and you get 8 over 9. So if you want to simplify, you can. Probably should for my lab. But that's it. You can just look at the number of male students. It's your bottom number. And the passing, instead of looking at all the passing people, since we know we're just looking at male students because we know we're going to get a male student, that was the given, we just look at the passing males, which ended up being 16 of them. Okay, I'm going to do this one more page. We'll do this one more time, show you this, and then we're done with this section. Okay, so start off. I got an instructor. I got a chart, and it shows all the different numbers for how many different types of professors there are, full professors, associate professors, instructors. Shows their age ranges from under 30 all the way up to over 60. And they first off want to find the probabilities. We're looking for probability of an instructor. So we're looking for instructors. That's going to be this group right here. This is your instructors. Notice that there are 33 instructors out of this whole group of 1164. So if they want just a straight probability of instructors, we just do 33 out of everybody because we're just doing the whole group. We're not limiting it. We're not doing any givens. So 33 out of 1164 is the probability of getting an instructor. Second part. For the second part, we want to look for someone in their 30s. So we're looking for someone in the 30 age range. So 30s is going to be this age range right here, 30s. And notice there are 402 people in their 30s. So again, since we don't have any given, we're just looking for someone in their 30s. We have 402 options that are in the 30s out of the 1164 total options. Without givens, it's pretty straightforward. You just count the number of good options over the number of total options. So typical probability style. We get to the next part. Now we have to look at and say, we're looking at someone being an instructor, given we know they're going to be someone in their 30s. So now we're restricting ourselves. Now instead of looking at the whole chart, we're looking at just the 30s range. That's our restriction. So we're doing the probability of an instructor, given they're in the 30s. So first off, we want to think about the number of good options. Well, for the number of good options, the instructors, there are 17 instructors out of people in their 30s. Again, I'm limiting this just to people in their 30s because that's my given. So I have 17 good options out of 30s. Well, the 30s gives me 402 options. I'm not going to look at the whole group anymore because I know I'm looking for someone in their 30s or out of the people in their 30s. So that's why I'm just going to have out of 402. So my probability, again, I tweaked this because I knew I was working out of the 30s. That's how I knew it was going to be 402. And I was just using 17 because I'm only looking for instructors in their 30s. I'm not looking at all the instructors, just the instructors in their 30s. That's how I got that 17 out of 402. Let's try one more. So I've got faculty member in their 30s. So now I'm looking for someone in their 30s. So some probability of someone being in their 30s. Given They're an instructor. So I know that this person's going to be an instructor. That's my given. They're going to be an instructor. I want to see what's probably going to be in the 30s. So if I look at my instructors, what's the chance of the 30s? Well, there's only 17 of these instructors that are in the 30s. So there's only 17 good options, 17 instructors in the 30s. And so I'm looking at only instructors. There are 33 total options because there's only 33 instructors. I have 17 over 33 for that one. So again, these conditional probabilities, you have some kind of condition that's requiring. And so instead of looking at the whole chart, the condition limits us to just the one part. So we knew that it was given instructors, so we just looked at the instructors. That's how we got that. So that's our conditional probability. Again, it's not doing more than one thing. It's only doing one thing. We're only finding the probability for like one actual picking a person, but we have some kind of given knowledge about them. That's what this given does for us. Okay, so that's out this section 4.3. We're getting pretty far in our probability. We have one more section to go in probability. As always, if you're having problems with the homework, you need help, make sure you're using that Ask My Instructor button. I've been getting a few homework questions where people just email me questions without using the Ask My Instructor button. That works fine. I'll still answer those questions, but if you use the Ask My Instructor button, then I can actually look at the homework problem a little bit more directly, and I can probably provide a little better feedback. So Ask My Instructor button in my lab is a great way to ask questions. It's only on the homework, not the quizzes. So if you do have a quiz question, you can just like screenshot it, send it to me. That's fine. But the homework, I really recommend using the Ask My Instructor button to ask questions. Okay, I will see you on the next set.